Okay, so I'm just going to go through the topics that you can expect to see on the midterm exam, and if you have any questions, certainly don't hesitate to ask in the chat window. And if anybody else is watching this, if they want to send me an email, profsullivan360@gmail.com, I have my email account open and I can take any questions that there are. All right. All right, so the midterm exam, hang on just for a second. Midterm exam is going to cover chapters 1 to 3 and 5 to 7. And you can bring an 8.5 by 11 sheet of notes, both sides with notes, formulas, examples. You can also use your calculator. Some students find that it's helpful to write the steps for their calculator on the cheat sheet. There weren't a lot of the features of the calculator that you're going to be using, but there were some, and I'll go over those as we kind of go through the topics. So in Chapter 1 was an introduction to the course, and talked about what statistics is. Statistics is the science of making sense of data. And data is just basically information about people or things. Had some terminology in this chapter as well. You should understand the difference between a population and a sample. You can think of a population as being the complete set of items that you're going to be studying, whether they're people or things, and then a sample is a subset of that population. Do you know why samples would be used in statistics? I don't want to put you on the spot, Marcy, but you're my only right now viewer. But why would you use a sample in statistics? Yeah, exactly. That's right. So usually the populations are very large, and it would take too much time or money or effort to gather data from the entire population. So you look at a subset, and you kind of hope that by using proper statistical methods that your sample is representative of the population, so that when you when you look at that sample, when you study that sample, you'll then be able to draw conclusions about the larger population. So definitely understand that. And then we also looked at the idea of a parameter versus a statistic. And you can think of a parameter as a number that describes a population. So it's a number that describes a population. And examples of parameters would be population mean, which would be mu, a population standard deviation, which is sigma. And we're going to see in the upcoming chapters population proportion. Those are all parameters. So those are numbers that describe the entire population. And usually these parameters are not known because, for that reason that we talked about before, that populations are just usually too large to study completely. So a parameter describes a population. So we usually estimate a parameter with a statistic. And a statistic is a number that describes a sample. So examples of statistics would be the sample mean, x bar, the sample standard deviation, which is S, and then we're going to see, you haven't seen the sample proportion, but the sample proportion is going to have the symbol p hat. So don't worry about p hat right now, but basically the idea is just that you're going to be using a number from a sample to estimate a parameter, which is a number that describes a population. Any questions so far? Okay, is my writing big enough, or should I write larger? It's fine. Okay, great. All right, so we looked at different types of data. You feel like a mute. That's funny. Well, this is actually good because I was wondering if, well, first of all, I'm glad that I have somebody participating because this is, I wasn't sure if I'd have anybody participating, but then not everybody's going to have a microphone, so it's good for me to know that I can have the screen up and be able to interact via chat window. So again, I really appreciate your participating. Okay, so we looked at types of data as well. Okay, so the first distinction you want to be able to make is qualitative data versus quantitative. And the way you can keep this straight is qualitative begins with the word QUA, or the prefix qual, which is similar to quality. So qualitative data would be data collected about the quality of some sort of object, whether it's a category that it would fall in, or a name, or a label. Whereas quantitative, it begins with the prefix quan, like quantity, and that indicates a number. There are two types of quantitative data that we looked at: discrete and continuous. Discrete data represents usually counts, and continuous data represents measurements of some sort. Okay, so for example, if I'm counting the number of cars passing over the Sagamore Bridge in a given day, that would be discrete. If I'm measuring the height of heights of 7-year-old girls, that would be continuous data. So on the midterm exam, I might, give you a variable, and I'd say, is this variable qualitative, is it quantitative discrete, or is it quantitative continuous? So, and you would have seen this on the practice exam as well. You should be able to categorize data in this way. All right, now moving into Chapter 2. In Chapter 2, we talked about organizing and displaying data. And the first way that we talked about organizing data was into the form of a frequency table. And you can organize qualitative data into a frequency table. So for example, maybe you survey 100 people and you ask them their blood type. And there are 4 different blood types. And you basically count the number of type O's, the number of type A's, type B's, type AB's. So maybe you have, let's just say, 45 type O, 40 type A. Oh, now we have too many here. Let's say 10 type B and 5 type AB. And that would be a frequency table. Extra credit? What do you mean extra credit for what? Oh, extra credit for participating? Is that what you mean? Yeah. Oh, I see. Okay, yeah. Sorry, I just saw you. I just saw the chat window. I apologize for that. Yeah. Okay. Now, do you remember how to get the relative frequencies? How would you get the relative frequencies here? Yeah, exactly. So I've made it easy here. I said you can add this up to, or this adds up to 100%. So You know, and I'll take either decimals or fractions. Okay, so that would be the relative frequencies. So this is the proportion of times that we, observed each blood type. And eventually, when we got into Chapter 5, just kind of looking ahead here, we could use these relative frequencies as an estimate of the probability that an individual would have each type of blood. So if I were basing it off of the sample of 100 people, I would estimate that the probability that somebody has type O blood, I would estimate that probability to be 0.45 or 45%. So you can build a probability model from this frequency table. So that's an important connection to make. All right, so that's a way to organize qualitative data because blood type is qualitative. You could also organize quantitative data in that same way. And we looked at two different types of quantitative data, discrete and continuous. This is qualitative. So quantitative discrete is counts. So maybe I count the number of people waiting in line at a given point in time at a bank. That would be discrete. So this is one way to do it. I can just have single numbers in this first column. Again, just making this up. 4, 5, 6, 5, or something like that. So those are individual numbers. And I think in the project, I don't know if you have any questions about the project, but in the project I asked you to create one frequency table that looks like this that has individual or single numbers in the first column. You haven't started yet? Okay. So I asked you to make one frequency table, sorry, not single column, single values. And then sometimes you can put in ranges of values. So if I say, distance from school or something like that, maybe we'll look at quantitative discrete data. I'm sorry, quantitative continuous data. So let's say distance from school. You could say, 0 to 4 miles, 5 to 9 miles, so on and so forth, where these are called classes. So you would do this if you had a lot of distinct values in your data set and you didn't want to list them all out individually. You'd create ranges of values, which are called classes. And it's important when you do this that your class widths are the same. You don't want to have some very narrow and some very wide. Do you know what the class width would be for this particular frequency table? I don't know if you remember. Yeah, it's 5. Good, excellent. Most people would say 4, but you're right on target. It's 5. It's the distance between subsequent lower class limits, which is 5. And it's also the width of the bars on a histogram. All right, I'll just make some numbers up here. Okay, so that's organizing data into tables. And then we also talked about different ways to display data. So for qualitative data, we looked at a bar graph. Most people are familiar with that. Just make sure you can do both a relative frequency bar graph and a frequency bar graph. Frequency or relative frequency. This doesn't go with this blood type. Maybe I should make it go with that one. Hang on. So if I had blood type, okay, so it's a bar chart. I think most people are familiar with bar charts. It actually, and then again, make sure that you can put you can also create one that has relative frequency on the vertical axis as well. That's another one. And then we also looked at pie charts. So that would be something else that you'd need to be able to do for qualitative data. And then for quantitative data, we talked about histograms. If you have single values in the first column, you just center the bars over each of the numbers. I'm just going to start my numbering here just so I don't have an axis going right through. 2, 6. Okay, so whatever this is, this would be frequency. One thing to notice is that with the histograms, that's a histogram, the bars will touch. With a bar chart, the bars don't touch. And then with the histogram for this one, the way your book is doing it, they're having you label the lower class limits. So if this is distance, so what I just went through and I read off the lower class limits, 0, 5, 10, 15. Put 20 here. So the way you would read this, you would say there are 4 values from 0 up to but not including 5. So it's up to but not including. This is one way to do it. Other books will show you different ways, but this is the way that your book is showing. Do you have any questions about that? So again, these are lower class limits. Okay, great. All right, talked about different histogram shapes. That's really important. Hang on just for a second. I have to figure out how to move this. Oh, there we go. Okay, histogram shapes. So you could have a symmetric shape histogram. And the reason that, so that's symmetric. That's a histogram with a symmetric shape. The reason why this is going to be important is that in the next chapter we're going to talk about calculating statistics, and some statistics work better with symmetric distributions and some work better with skewed distributions. So if your histogram has a long right tail, it's called right skewed. If it has a long left tail, it's called left skewed. And what we're going to see in Chapter 3 is that having these either extremely large or extremely small values will affect some statistics and not other statistics. For example, the mean will be affected by very large or very small values, whereas the median will not. So that's why it's important to know different histogram shapes. We also looked at bimodal and uniform. Bimodal means having 2 modes or 2 peaks. And what that usually means is you have a couple of different populations mixed together. For example, if you had heights, a data set containing heights, and it were bimodal, that might mean that you have, say, heights of boys and heights of girls of a certain age, and the boys are, say, taller on average. So they kind of are on this end and the girls are on this end. Now uniform would just be bars of the same height. Okay, and that pretty much, we also looked at stem and leaf plots. Make sure you can do those. Dot plots you did look at, but you won't be responsible for those on the test. So I'll just stop at this point and see if there are any questions. Okay, so on to Chapter 3. sorry, numerical summaries of data. Okay, so once you've collected your data, you've organized it into a table, represented it by some sort of graph or some sort of display, you can go ahead and calculate some numerical summaries. So the things that we're going to be interested in, the characteristics of a data set that we're going to be interested in are center, variation, or variability, also called spread, and then position. All right, so by center we mean what is a typical value in a data set? What is the average value in a data set? By variation or spread, we mean are the values clustered together around the center, or are they all spread out? Oh, I thank you. I just read what you said in the chat window. I appreciate that. And then position. We want to know where a value is relative to other values in a data set. So, for example, if you've ever taken a standardized test before and say you score in the 70th percentile, that means if you compare your scores to the other scores in the data set, your score is higher than 70% of the scores in the data set, and it's lower than 30%. So measures of position. And then we're also going to be interested in outliers. And outliers are extreme values, either extremely low or extremely high values. And there is a formula for computing what are called fences. And if values are outside of those fences, they're going to be considered outliers. So we'll talk about that as well. All right, so there were 3 measures of center, again, which means average, that we looked at: the mean, the median, and the mode. Just scoot this down a little bit. All right, looked at 2 different formulas for 2 different means. First is a population mean. And the symbol for that is mu. And this is a parameter, so remember before we talked about how parameters are numbers that describe populations. And to get that, you add up all the values in the data set, so that's sum the x's, and divide by the population size. So this means sum x is a value in the data set, and then n is population size. You know, and most people can do this without the formula, but you know, we like to put some formulas in because it is a math course. So that was the population mean. Now we don't usually know what the population mean is because the populations are usually too large. So to estimate the population mean, we compute the sample mean, which is called x bar. And here we're adding up the values in the data set and dividing by the sample size. We also looked at the median. And the reason that you might use the median instead of the mean is that we said that the mean is not resistant to extreme values. So even if you have just one extremely large or extremely small value in your data set, that's going to affect the mean. So we say it's not resistant. The median, on the other hand, is. The median is resistant to extreme values. And the median is just the middle value in a set of ordered data. So that's actually a common mistake that people will make on the midterm exam, is they'll forget to put the data in order. So just make sure you put the data in order, just count into the middle. If you have 2 numbers in the middle, you just take the average of the 2 numbers. You would use the median if your data were skewed, and that's something that you want to try to understand. If you have skewed data, what's the relationship between the median and the mean? So this is a, imagine, right skewed data set. The median is going to split this data set in half, where half of the area will be on one side and half will be on the other. And then these values up here are going to pull the mean away from the center, so it might be somewhere like right here. So if you have a right skewed distribution, the mean is going to be larger than the median because of these values up here. And likewise, if you have a left skewed distribution, the mean will be smaller than the median because those small values are pulling it away from the center. All right, so those are measures. Oh, mode. I didn't talk about mode. Mode is the most common value in the data set. We didn't really do a whole lot with that, but it's something that you should know. All right, moving on to variation and spread. So the basic idea with that is that we want to get an idea of if the values are really clustered around the center of a data set or if they're all spread out. And the most basic measure of variation is called the range, which is just the max minus the min. Maximum value minus the min. But the problem with using the range is that it's really affected by either very large or very small values, just like the mean was. If you have even just one large value in a data set, it's going to skew the range. So that's why we'd like to incorporate every value in the data set. And the standard deviation and the variance do that. So let me just go over, sometimes the standard deviation confuses people. I don't know how you feel. How do you feel about that? Do you feel comfortable with the formula, or should I go over that? You're okay usually? Okay. I think I'll just go over it briefly though, just in case anybody wants to watch this sort of after the fact. So the basic idea is that, let's say you have a data set. I'll just do a dot plot here. And the data set is 1, 3, 5, 7, 9. All right, and so here we are, 1, 3, 5, 7, 9. And you could find the average of this data set, the mean of this data set. So you can add up all the numbers. And if you add up 1 plus 3 plus 5 plus 7 plus 9, you'll get to, let's see, 9, 18, 25. Divide by 5 numbers. So the mean here is 5. And we want to get an idea of how spread out the values in the data set are from the mean. So you look at, say, the number 1. You say, how far is that from the mean of 5? Well, it's 4 below the mean. So we say that the deviation is minus 4 because it's below the mean. So that's the deviation. If you look at 3, 3 is 2 units below the mean of 5, so we'd say that the deviation is negative 2. If you look at the value 5, that is the mean, so the deviation is 0. 7 is 2 units above the mean, so the deviation is 2. And then 9 is 4 units above the mean, so the deviation would be 4. So the basic idea is, so we get an idea of how these values are spread out. Some of the ones that are farther away have a larger deviation. And then what we're going to do is we're going to square all these deviations and sum them up. So the formula for this, and let's just look at the sample standard deviation, which is S. The idea is that you're going to put all of the values in the first column. In the second column, you put the deviations. Then you'll square the deviations and sum them up. Okay, so 1 minus 5 is negative 4. Fill these in. This is all the deviations that I wrote in red over here. square all the deviations. Okay, and then add these up. Okay. Oh, and actually, you know, I have the formula wrong here. Square root. I knew something looked wrong. Okay, so sum up all of these squared deviations. So that's equal to 40. Now here, n is 5 data values. So 5 minus 1. And we wind up with square root of 10, which is 3.2. All right, so that's the sample standard deviation. This you could also get on the calculator by using one-var stats. Okay, so it would be stat, calc, one-var stats. And as long as you have it in L1, you can see the sample. As long as you have the data in L1, you can see the sample standard deviation is 3.2 rounded. In order to get the variance, you would just square that. You can also see that you can get the mean from this, and you can get the median. So that's a very handy thing to be able to use. Okay, so back to this. Another measure of center, which is resistant to extreme values, is the interquartile range. Okay, interquartile range. So interquartile means, inter means between. Quartile, we'll talk about in just a minute what's a quartile. And then range is the distance between two values. So we're going to look at the distance between the quartiles, and specifically the first quartile and the third quartile. So what are quartiles? Well, quartiles basically split a data set into quarters. All right, so if you had a data set that ranges from some low value to some high value, you know that the median splits the data set in half. And then if you split the lower half of the data in half again, that's the first quartile. And if you split the upper, that's not exactly right, upper half of the data, that's the third quartile. So about 25% of the values are in each bin, or whatever you want to call it. Okay, so that's what the quartile is. Quartiles are. So the interquartile range then is going to be Q3 minus Q1. It's the middle 50% of the data. So the idea is that even if you have a very large value out here, it's not going to affect the interquartile range. Okay. Now this falls under the position category as well, because the quartiles will tell you where a value is relative to the other values in the data set. So you should know how to calculate quartiles. You should also know how to interpret percentiles. So as I mentioned before, test scores are where we often see percentiles. If you're in the 70th percentile, your score is better than 70% of other test scores. Another measure of precision is something called a z-score. And to get a z-score, you take a value, subtract the mean, and divide by the standard deviation. And a z-score basically tells you how many standard deviations a value is located from the mean. So let me just do a couple of different examples here. One common example is IQ scores. They have a mean of 100 and a standard deviation of 15. So if someone has an IQ score of 115, what's the z-score associated with that? What would the z-score be for that? Can you tell me? Even without using the formula, how many standard deviations away from the mean would that be? Yeah, exactly. All right, so you take the mean and go up one standard deviation to get up to 115. So one standard deviation above the mean. If you use the formula here, value minus mean over standard deviation, which would be 1. So if you have values above the mean, they'll have a positive z-score. Values below the mean will have a negative z-score. And values that are right at the mean would have a z-score of 0. So you should be able to calculate those. I just want to point out that one common mistake that people make when calculating z-scores is they forget about order of operations. So if sometimes people would calculate something like this, and they get a really large number. And the thing to remember is that if you're going to do this all at once, oops, 115, you need to put parentheses around the numerator. We also looked at outliers. Oh, unfortunately my pen just stopped right. Oh, here it comes back again. Been having trouble with my stylus. Okay, outliers. So outliers are extremely large or extremely small values. And so the idea is that you're going to calculate some fences. And if a number is outside of those fences, it will be considered an outlier. All right, so that's pretty much chapter, oh, one more thing, I just thought of it, box plots. Make sure you draw your axis and label your axis underneath the actual box plot. But a box plot uses the 5-number summary to show the distribution of a data set. So you draw a box that extends from quartile 1 to quartile 3, draw a vertical line at the median, and then draw whiskers that go down to the minimum and up to the maximum. Sometimes you'll see box plots that have asterisks. Asterisks are values that are flagged as outliers. And if you choose to do it this way, you would make the whisker go out to the largest value that's not an outlier, or to the smallest value that's not an outlier. So that's something that's called a modified box plot, and you have the option of doing that on the project. All right, so that's chapter 3, and then we went into chapter 5. I apologize, my pen has just stopped writing. Oh, there we go, it's back again. And chapter 5 was probability. We looked at 3 different approaches to probability. Looked at the classical approach, the classical approach you would use if you have equally likely outcomes that can be listed in a sample space. So if you are rolling a die, for example, and you have 6 equally likely outcomes, which can be listed in a sample space. You know, I might have to shut down my Windows journal because the pen's acting strangely. Bear with me just for a moment. Let's try to bring this back up. Okay, so 3 approaches. Classical. Oh, unfortunately, my pen, can you see this? My pen is not working right. Unfortunately, I was doing this in class as well. It's writing even though I'm far away from the screen. It looks cursive. I know, you know what's happening. First of all, the pen is kind of turning off on its own, which is too bad. But then the other thing it's doing, I think it's something with the screen. Even if I'm not touching the screen, right now I'm not even touching the screen, but it's still writing. So I don't know, I think I'm going to have to send it in to be fixed, but I'll do the best I can. So we looked at 3 different approaches. Classical approach, and again, I apologize because this is the pen. I don't know if I can even do this. Yeah, it's going to be impossible to write. It's trying to connect everything. Oh well, no, that's unfortunate. Anyway, we looked at, I'll just kind of talk you through, if that's okay, the rest of this, because I think I'm going to have to restart my computer. Is that all right with you? I think I may try this next on my iPad and get a stylus for it. So I'm going to have to send this in. Anyway, classical approach, empirical approach. Actually, you know what I could do? Let me just hang on just for a minute. Okay, let me try typing instead. Make it big enough. Can you just tell me if you can see this? Okay, so 3 approaches. So we looked at classical, empirical, and subjective. Okay, so the key thing again with the classical approach is that you're dealing with equally likely outcomes. And with classical, you can list a sample space. So we could do something like this. Roll a die, that's the probability experiment. You have 6 equally likely outcomes. And then you can create events, and we were using capital letters to represent events. For example, I could say A is the event that you get an even number, B is the event that you get an odd number, and I could say what's the probability of A. So you have 3 outcomes that are favorable to that event over 6 possible outcomes. I could also do probability of B. That would likewise be 3 over 6, which is 0.05. We also looked at complements. So I could say, what is a complement? Is there a superscript here? I'm using a superscript. Let's see. I guess I could use an equation, right? Except my pages. Well, all right, it's going to be a complement. The idea is a superscript, but I don't see quickly how to do that here. No, that's not right. That makes the text larger. Well, anyway, imagine that the C is a superscript. A complement equals 1. So the probability of a complement So what's the probability, for example, that you don't get an even number? So a complement would be the event that you don't get an even number. That's 1 minus the probability that you do get an even number. We also looked at probability of OR, the probability of one event or another occurring. And there were two different addition rules for probabilities involving OR. One is if you have mutually exclusive events. And that's if they have nothing in common. No outcomes in common. So this is an example. This up here is an example of disjoint events because there are no common outcomes shared between event A and event B. A number is either even or odd. If you do have common outcomes, you have to subtract the overlap to avoid counting outcomes twice. We also looked at the multiplication rule. And the multiplication rule is used for probability that one event and another both occur. And we looked only at the multiplication rule for independent events, I believe. So for example, if you have a basketball player that has a certain free throw percentage, the probability that he makes the first shot and he makes the second shot, let's just say his free throw percentage is 70%. What's the probability he makes 2 shots in a row? Equals 0.7 times 0.7. You should be able to work with contingency tables, which are basically, they're frequency tables, but they include data from 2 variables. Let's see what else from that chapter. Oh, yeah, the probability of at least one. The idea with that is that you're going to use the complement of at least one, because the event at least one means 1, 2, 3, 4, depending on what the situation is. So the complement of at least one will be none or 0. So what you want to remember is probability of at least one equals 1 minus probability of none. All right, so that was chapter 5. I'm noticing I have only about 6 minutes left, so I didn't watch the time very well on this, but I guess first time is, first time is always things are not always going to go well the first time. But anyway, okay, so that's the classical approach. We also looked at the empirical approach, and I alluded to that previously, and that was, if you had a frequency table and you computed relative frequencies for the different categories, those relative frequencies could be used as estimates of probabilities. And that's called a probability, create a probability model. And then the subjective approach was the third approach, and that's using opinion to estimate probabilities. All right, so we got into then chapter 6. And chapter 6 was discrete random variables and discrete probability distributions. Again, where these discrete random variables usually represent counts. So the idea was that you could create a table of values where you have your values of x in the first column, your probabilities in the second column, and as long as those probabilities add to 1, and each of those probabilities is between 0 and 1, then you have a discrete probability distribution. We talked about computing the mean and the standard deviation of a discrete probability distribution. And then also using the calculator to find the mean and standard deviation. And the idea with that is that you would enter the values of x in that first column. If it's 1, 2, 3. And then you would use one var stats. Making sure you use L1 and L2 to compute the mean and standard deviation. We looked at a very special case of a discrete probability distribution. That's called the binomial probability distribution. Binomial probability distribution uses a special formula to generate probabilities. And the general idea with a binomial probability distribution is that it answers the question, what is the probability of X successes in N trials, where the probability of success is P? So what's the probability that a couple has 3 children and they have exactly 1 boy, for example, where the probability of a boy is 50%? Or what's the probability that in a sample of 4 voters, exactly 2 support new legislation, for example, where overall 80% of people support the new legislation? So anywhere where you have a situation where you have a number of trials that are independent and the probabilities are the same from trial to trial, and each of the trials results in one of 2 outcomes, that's a binomial experiment. So for the test, I'm going to ask you to use the formula on some of the questions, but you can also use binom PDF to generate probabilities. That generates individual probabilities. And binom CDF generates cumulative probabilities. Right, so that's that. Oh, and I skipped over expected value, but expected value is basically the mean of a probability distribution. It's just expected value is used when you're dealing with money. All right, so that's that. And then the normal distribution was the most recent one. And I don't know if this is going to shut off automatically in 1 minute, but we'll do that very, very quickly. Chapter 7. I don't want to keep you too long. I have it scheduled till 9 o'clock. So do you happen to know if it just shuts off automatically or? Tough learning experience. You got that right. That's okay though. I have to figure out why my tablet is doing this though. It's really causing problems. Okay, so in chapter 7 we started to get into continuous probability distributions, where the random variable is a continuous random variable. And the one that you looked at was the normal distribution. So you should be able to sketch a normal distribution where you put the mean in the middle. And then under the inflection points, going up 1 standard deviation and down 1 standard deviation, you'll be under the inflection points and be able to label that, 1, 2, and 3 standard deviations out. And then you talked about finding probabilities under a normal curve using normal CDF. Say finding probabilities under the normal curve. You should also be able to use inverse norm to find z-scores. You can either use it to find z-scores or you can use it to find percentiles. And that's pretty much it. So do you have any questions on anything? You have no clue? You have no clue about? Yeah, and you know what? One thing I just realized that I forgot was the empirical rule. Are you familiar with the empirical rule? That was the 68, 95, 99.7. Were you? Yeah, okay. Yeah, so that's if you have data that are normally distributed, one standard deviation away from the mean, if you create an interval, that will include 68% of the values, approximately 95% if you go out two standard deviation, 99.7. I'm trying to think of anything else that I didn't include here. And I'm sorry it was so rushed at the end here, but I didn't really watch the clock. So yeah, let me see. There's a red button at the bottom. Bear with me just for a minute. See what it says here. Stop broadcast. I think, no, I'm actually still broadcasting, believe it or not, so that's interesting. Did you have any questions about anything? Calculator, StatCrunch project? Ah, okay. You like are you a technology person? Yeah, you like technology. That's why you're taking an online course, right? You find the book confusing though, huh? Yeah, yeah. I know it's interesting. Some people learn better via video and some people learn better by reading. I think I'm more of a video person right now, actually. If I can find a good video, I spend a lot of time on YouTube. I think that really makes it clearer. But definitely, if you have any questions, please contact me. And have you looked at the practice test yet? It's your second online course. Okay, that's good. What did you take previously? From Calc. Okay, great. All right, well, I'm going to stop the broadcast. I do actually see some other people are watching. Oh, terrific. That's great. And again, I really, really appreciate your participating. And maybe the next time we do this, we'll get more participants. All right, so thank you very much, Marcy. I appreciate it. Have a good evening.